at the University of Arizona. He has done research on observational cosmology, in particular, low surface brightness galaxies, the intergalactic medium, and the surveys of active galaxies. His team has also discovered the largest spiral galaxy named Malin 1. He was a frequent user of the Hubble Space Telescope in the early days. In addition to that, he has also written over 50 popular articles on cosmology and astrobiology, including two introductory textbooks and 8 novels. So please join me in welcoming Chris Impey. For today's session, most of our participants have already submitted their question using the registration link. Now we shall start our session by discussing what is cosmology and astrobiology in brief. So I would humbly request all our participants to mute themselves and turn on your videos for a peaceful interactive session. Over to you, Professor Chris. Thank you so much for joining us.
Okay, I'm very pleased to be with you. This is a new group for me, and I can say I have been to Nepal one time 30 years ago, a long time ago. I went and did the trek. I flew into Lukla, and we went to Everest Base Camp, and I went up to Kalapatar, and had a beautiful time. I spent some time in Kathmandu at the end. So, but that was a long time ago.
You are always welcome here. Please visit us soon.
I would like to come back. Traveling, as you know, is still difficult. Right, so I think I will spend 5 or 10 minutes each on cosmology and astrobiology, give you my sense of where these fields stand in terms of research and what we know and what we don't know, and then leave, half the time at least for questions so that you can explore things you're interested in. My main expertise is more in cosmology than astrobiology, but I've written a lot of articles and books and go to conferences on astrobiology, so I know quite a lot about that field too. Cosmology is the study of the universe as a single entity. It's the study of the history of space and time and the contents of the universe. So it's a very big and ambitious subject to understand the universe we live in on the largest scale. I would say the last 30, 40 years have been very successful years in cosmology with many new innovations, mostly driven by large observational facilities, the Hubble Space Telescope, of course, but also very large telescopes on the ground, much larger than the Hubble, in fact. So cosmology, often requires big telescopes like gathering power, but also multi-wavelength methods. And so the technology of astronomy has benefited this subject a lot. The theoretical side of cosmology is also advanced, but maybe not quite as much, because the theory of the universe we have has been in place for more than half a century. So I guess the way I should start is to just say, what is the status of the Big Bang model of the universe? The Big Bang model, it's important to remember what the Big Bang model does say and does not say. Not theories of the universe are not complete. The Big Bang model describes the evolution of the universe from a hot, dense state 13.8 billion years ago, which we take to be the origin of space and time. So I'll say right at the outset that the Big Bang model from the beginning never claimed to say why the universe exists, what caused the expansion, or what lies beyond the universe we live in, or before the universe evolved 13.8 billion years ago. So this is not a problem or fault of the theory. It's just the limitation of the theory. And some people forget that, so it's important to remember at the beginning. In terms of the model, though, it's very successful, very successful. So the Big Bang, our belief that this is the correct description of the universe rests on foundations that are strong and have only got stronger over time. Obviously, the first foundation is the expanding universe, measured by Hubble in 1929 for the first time, and then since by many observers looking at galaxies that extend to 10 or 11 billion light years away. So this cosmic expansion where there is no center that can be identified, every galaxy moves away from every other galaxy. There's just no reason to ask, or you cannot ask or even answer the question of where's the center. There is no center, because all parts of space and time were part of the original event and continue to be part of the event that it's now long ago in a universe that's old and cold. So the Hubble expansion is the key indicator that there was a different state of the universe in the past. The evidence that probably cemented the model for most people was a microwave background radiation discovered accidentally in 1964, although it had been predicted in the 1940s by George Gamow, quite accurately, in fact. He predicted it. It just was not possible to observe it. In 1940s, we had no microwave telescopes. That was detected, and since 1964, the satellites that have studied it have improved in sensitivity by a factor of almost 1 million. So incredibly detailed observation of the microwave background. And these reinforce the idea that this is the radiation left over from the Big Bang. We see the universe in this radiation as it was 400,000 years after the Big Bang, when the universe was 1,000 times hotter, 1,000 times smaller, and 1 billion times denser. And every detail of this radiation affirms the Big Bang model, and then goes beyond that to suggest that we can see the seeds for galaxy formation in this very early radiation from the very slight variations in temperature and intensity in different parts of the sky. But basically, it's very smooth radiation, the same temperature and intensity within one part and 100,000 wherever you look on the sky. The third piece of evidence for the Big Bang is the fact that the helium in the universe is too much to explain by the process of stars and their fusion of hydrogen to helium, the way the sun is doing. If you calculate how much helium could have been made by all the stars and all the galaxies we see, it's by far insufficient to explain the fact that the universe is 1/4 by mass in helium, or 1 in 9 atoms or helium nuclei. The Big Bang, however, explains this perfectly, because the universe in the first few minutes was the temperature of the interior of the sun, and fusion occurred, and helium and other light elements, lithium, beryllium, were created. And the measurement of those abundances of those light elements in different settings agrees very well with the Big Bang model. So that's a piece of evidence not quite as familiar as the radiation, microwave radiation, but also strongly supports the model. And then, of course, we see the fact that galaxies evolve. So if the universe was in an earlier, denser state, then the galaxies have not always been the same. And we see now, through observations across cosmic time, galaxies assembling into large galaxies like ours from smaller galaxies. And we see evidence directly, actually, that the universe was hotter and denser and has been evolving for all this time. So although people occasionally say the Big Bang model has problems and that there are some issues, just important to remember that if you throw it away completely and have some alternative theory of the universe, you have to explain a lot of evidence, a lot of data, and it's very hard for an alternative theory to do. The bar is set very high to replace the Big Bang completely. Okay, so that's the status. But now what are the issues around the Big Bang that remain? Well, they revolve around the things that the Big Bang never explained, was not designed to explain. The only adjustment to the Big Bang model in half a century has been the idea of inflation, the idea of a very rapid exponential phase of the universe's growth when it was a tiny fraction of a second after the Big Bang. This event is used to explain why the universe is spatially flat, why the curvature of the universe on large scales is almost zero, and also why the universe is smooth, why that radiation is the same temperature and intensity in every direction you look, very precisely. Inflation does that by smoothing out and stretching the universe early on. And inflation leads to an implication that the physical universe, all there is much bigger than the visible universe, all we can see. Because when we look at the universe, we do not see an edge in space. There is no edge. There's just an edge in time as we look back, when we eventually look back towards the Big Bang itself. So inflation hypothesizes a much larger physical universe than the part of it that we can see, which contains 200 billion galaxies. So it's a big universe with a lot of material in it and radiation. What is the support for inflation? it's pretty good, but not perfect. So I would not say inflation is proven beyond any doubt. There's some evidence to support it. Of course, the universe is flat and smooth, but that was why inflation was developed. So you can't give it credit for the things that it was designed to explain. You have to look for other evidence for inflation. And detailed observations of the microwave background do indeed support inflation at some level. I mean, the inflation makes some predictions, but inflation is not one thing. Remember that inflation is based on a mechanism for this exponential expansion that is not really understood. The cause of inflation, the physical cause, is not completely understood. It's thought to emerge from the merger of the forces of nature in the early universe, but we do not have a good physics theory for that. So inflation is an idea, and the explanation of it, or the theoretical development of it, goes in a number of different directions. There are variations of inflation, and so it's which one are you testing? So some tests of inflation have been made, and they're moderately successful. No observation has refuted it, but the most critical and important observations still remain to be done, and they could be done in the next 5 years with really good observations of the microwave background from the South Pole and from other space observatories. So the test of inflation, the full test of inflation, still remains in the future, near future. And then the other things that the Big Bang doesn't explain, the cause of the inflation, the cause of the expansion itself, there's speculation about that. There are theories that try to go beyond our universe because they recognize that if inflation is correct, the universe started as a quantum entity, as a quantum fluctuation, essentially, in a vacuum situation. And in that vacuum situation, you may have other fluctuations and other space-times emerging, and that's the idea of the multiverse. So people have tried to go beyond the Big Bang to imagine a multiverse, a series of events, maybe going back forever in time, without the Big Bang being the beginning of all history of the universe in the large sense. But these are very uncertain. The theories are uncertain, and the tests of the theories are not there yet. So people you'll read articles about the multiverse and about space-times beyond our own and so on, and the cause of the Big Bang. Should always remember these are very speculative. They're not in the mainstream of the science to be in the textbook as things everyone should know yet. They might be, but that's in the future. Very challenging theory also, and very challenging observations to test this idea that there are space-times beyond our own. How would you possibly know this? The only idea, I'll just put one idea out, people think there might be an imprint in our space-time, our universe, in terms of gravitational radiation, gravitational waves from other space-times. That's a possibility. Again, not very precisely predicted by the theory and certainly not observed yet, but it's an idea people will follow. So the state of the Big Bang is very healthy, very good, and people are trying to push the theory to its limits, try and ask big questions about it. Now, you may also read there are tensions in the Big Bang model over the fact that the rate of expansion we measure in the local universe doesn't completely agree with the expansion rate inferred from the radiation, the microwave radiation, which is obviously measured at a much earlier time. If we have a model of the expansion history of the universe, we should know the expansion rate at every age, at every stage. And these early and late measurements of the Hubble constant, the expansion rate, do not completely agree, and it's a persistent problem. It's not yet clear. People react differently to this situation. Some say it's a crisis in cosmology and will cause the downfall of the Big Bang. I'm not so sure yet. The data is very difficult to understand fully. It's not clear that people with the data understand all their errors and their systematic errors especially. So I think it's premature to use this tension, as it's called, the Hubble's constant tension, to say there's a real problem in cosmology. There may be, but it's too early to say. It's an example of the fact that people are trying to develop the model more fully and more precisely. The other foundational uncertainties of the Big Bang, of course, relate to the ingredients of the universe. The two primary ingredients of the universe are dark energy and dark matter, and we do not have physical understanding of either. We're, I would say, much closer to understanding dark matter because the observations of it astronomically have been going on for almost half a century. And we've measured it on many different scales. We've seen dark matter that holds galaxies together, dark matters in intergalactic space across the universe, on all different scales. And we've mapped it out using gravitational lensing and other methods. So there is very little doubt that dark matter exists, that something that has gravity but does not emit or interact with radiation exists. And it dominates normal matter by a factor of about 6. We don't know what it is. We've ruled out various things, black holes, substellar objects, planets, dust, almost everything except subatomic fundamental particles. And so that's where the search rests, primarily in physics experiments, to try and identify several promising candidates for a dark matter particle. And that also may succeed in the next 5 years. In fact, if it doesn't succeed in these physics experiments, that will be a crisis in cosmology and probably in physics too. So that's an interesting stage for dark matter. But there is progress being made, even though we don't know what it is. Dark energy is much less certain. We do believe that there is something in the vacuum that is causing the universe to accelerate in its expansion. That was a discovery of 1995 that led to a Nobel Prize some years later. But we don't know what it is. And we don't really even have a good idea of what it is. There are probably 200 theoretical papers a year written on dark energy, but they're very speculative. And the observations are very limited of dark energy. We don't think it varies in time and space, but they're not very good measurements yet. So our uncertainty over dark energy is really quite large. And the theoretical problem is large because the simplest ways physics can imagine energy in the vacuum do fail completely to explain the expanding universe accelerating completely. So this is interesting, depending on your perspective. It's either interesting and exciting for physics, or it's a problem for physics because the physics is not there and we don't know which way to go. So there's a lot of work being done on dark energy. And as I mentioned, the observational situation is challenging because improving the current measurements of dark energy is very difficult. There are strategies, again, with new telescopes in space and on the ground, but it's painful, slow work. So on dark energy, we are still quite unsure. So I think that's good for that. I'll obviously you can ask questions about anything, but that's the state of cosmology, more or less.
Yes.
Should I move to astrobiology, or do you want to take questions on cosmology now first and split
So
time?
I think we can take questions first because we have a list of questions prepared for
Okay,
you.
okay.
So I would like to begin from the question that we have in a chat section. Jim Slight is asking, how do you explain the fact that the CMB can be seen in all directions and all the space is expanding in all directions if there is not a central point for the start of the expansion?
Well, we start with the observation. So the observation made by Hubble and again by many people since is that almost all galaxies have redshift, which is a recession velocity. And his foundational discovery, the Hubble relation, means that the further away the galaxy, the faster it's moving away from us. And that is best understood in terms of a linear expansion of space-time, where you imagine space-time as some invisible medium in 3 dimensions that expands uniformly at every place. And then every object within that space-time, galaxies, are just carried apart from each other. So if you recognize that as the mechanism, expanding space-time, carrying galaxies away from each other, and recognize that we have not seen an edge to the universe observationally, so there's no reason to propose something that is not required by observation, then you see there's no special position in the universe. Our galaxy sees galaxies moving away from us, and a distant galaxy will see the same thing. They're all positioned. It's a democratic situation. Everyone sees the same thing. And therefore, the corollary is there is no center to the expansion. Because again, if you want to claim a center, you have to show why there is a center. And the uniform expansion suggests, no, there is no center. Every galaxy sees itself as the center, and therefore there is no center identifiable. So whatever happened at the beginning of the universe happened to everything, because running the clock back 13.8 billion years, all parts of space and time were contained in this one event called the Big Bang. And then everything emerged from that. and space and time unfolded over 13.8 billion years to the large, flat, and cold universe we live in. So again, there's no implied edge to the universe. There's no implied center to the universe. There's very important ideas in cosmology at the base of it.
So we have also our next questions about the cosmic microwave background. Um, where is that? So Akash Kuring is asking, can you please explain a little about cosmic microwave background cold spot?
Cold spot?
Yes, of
Oh,
cosmic microwave
yeah.
background.
So there's work on or claims of a cold spot. So the basic idea is that the microwave background radiation is expected to be almost uniform and smooth, the same temperature, same intensity everywhere. But the data is very accurate now. So we actually have the ability to look at very subtle, small variations in the temperature or the intensity across the sky. And every now and then there are claims of an anomaly, if you like, a situation where there's a variation in the microwave background that we wouldn't normally expect. And the truth is that most of these claims have just gone away over time. They've not proven to be anomalies that make you question the idea of the microwave background. So the cold spot in my mind is one of those. It's not at the significance level or at the level of variation that is a problem for the theory of the Big Bang itself. I don't think that's a problem. It could be an issue. There's one thing people forget, that we have only one universe to measure. So there's a variance or a sampling issue with the universe. And so because you only have one universe to measure, as opposed to a set of universes where you can take an average, you do actually expect anomalies. The quadrupole moment. So the universe has a dipole moment, like a magnet has a dipole, because we're moving in the Milky Way with respect to microwave background at some velocity. And we've measured that. And that gives a dipole variation. The microwave sky is hotter in one direction, in the direction that we're moving towards, and colder in the direction we're moving away from. We've seen that for decades. And there's also some other variations that can be caused just by the fact that we have one universe to measure and you have sampling variance. It's just a physics statistics principle. So that's why most cosmologists are very cautious about overinterpreting single anomalies or single pieces of the microwave background that seem hard to explain. There are some that we may not be able to explain because of this sampling issue. That's unfortunate, but true.
Our next question is from Ramesh, who is asking, what is the origin of hypervelocity stars?
So stars are mostly in binary systems. In our galaxy, we measure the star population, and we know that the sun is a little unusual because the majority of stars are either in binary or multiple systems. And as soon as you have stars in binary systems or multiple systems, you can have gravitational interactions that give a large amount of energy to one of the stars and essentially can eject it, give it more than the escape velocity of the galaxy. This is just standard gravitational physics. It's not anything strange. Energy is still conserved. It's just that you have multiple stars in the system. And so we know mechanisms whereby, especially in binary systems, but also multiple, you can give some stars extremely high velocities and kick them out of their star system, their stellar cluster, and then even from the galaxy itself. So hypervelocity stars are unusual, and we haven't seen that many of them, but the understanding of them is fairly simple.
So the next question is about the Big Bang theory, and it is from Sauzanya, and it goes like this: can science ever explain why the Big Bang happened? It is also in a bracket that I'm obsessed with this question, and I feel that question itself is unscientific, or this question falls into the field of theology and philosophy.
Yes, I mean, there's some point at which the origin of the universe may not be discoverable by us. Science is an optimistic pursuit. Scientists have made progress and understood many things, but there's no reason to believe we should ever understand everything. That would be arrogant almost, hubris. And one of the questions that's natural, which is what caused the Big Bang or what was before the Big Bang, turns out to be one of the very hardest to measure or to understand, because as I mentioned, the Big Bang model itself does not describe this. It doesn't include a cause or an origin or before. So you're reaching beyond the Big Bang for a new type of theory. And there are some theories about an endless universe based on inflation, for example, that happens endlessly over time and spawns universes over time where ours is just one. That's one idea. There are also some quite clever theories that actually finesse the idea of a Big Bang itself by using multidimensional spacetimes. So brane theory, it's called, or M theory, where, as you probably know, with string theory, we're postulating that there are higher dimensions of space-time, unobservable typically by us. And in those type of theories, you can have collisions between multidimensional, higher dimensional space-times where the energy in the collision generates a universe in 3 dimensions like ours. And so people have played with these theories and found situations where you can have an expanding universe that doesn't actually have a Big Bang in a sense of a singularity. So you can avoid the singularity, which is important because we don't understand singularities in physics. So that's a second idea that's in play that would actually not involve formally a Big Bang at all, but would have a cyclic universe. So there are cyclic universe theories now. And those are just 2 examples I give to say that there's a lot of theoretical work, very difficult theoretical work, but it's based on speculative physics, all of it. So we'd have to advance our knowledge of physics, fundamental physics, more to know if these theories are correct. And we'd have to be able to test the theories. And at the moment, that is challenging. I would say it hasn't been done. And some people wonder if it even can be done. I think it might be able to be done, but it's not clear yet. So yes, people are asking the question of before the Big Bang or what caused it with these different type of physical theories, but none are mature, I would say, theoretically, and none are tested yet.
So our next question is, sir, what was your take upon dark matter and dark energy and the analogy?
Can you repeat
It
that
is,
question?
sure. What was your take upon dark matter and dark energy and the analogy?
I
It
missed the last word.
analogy.
Hmm, okay, I guess I'm
So
not
it is from Raj Basil.
I'm not understanding the last word you said. You may have to write it in the chat or something so I can understand it.
Yes, sure.
Analogy, okay.
Sorry, I
That's okay.
mispronounced the word.
Analogy is fine. I know this is not your first language for everyone, but I guess I'm still not understanding the intention of the question. I talked about dark energy and dark matter.
So I would like to request Raj Basil, please unmute yourself and ask the question in your own voice so that you can make it more impact to the professor. Please, Raj Basil.
Hello there.
Yeah. Hello, I can hear you.
Sir, my question was, what was your take upon the dark matter and the dark energy, and the analogy between the 2?
Okay, so I did give us a little summary of dark energy and dark matter. As for the relationship between the 2, that is an interesting question, because at the moment it's not clear there is any relationship between the 2. Dark matter is something that we think is a fundamental particle, and that we have ideas of what it might be. So as I said, good progress and perhaps an answer to that question coming. And it's a particle that just interacts weakly with matter, but has gravity and does not interact with the electromagnetic radiation or that force. So that's quite a mature understanding, even if we haven't detected it yet. Dark energy, we're far less sure. Dark energy appears to be a property of the vacuum itself, of space-time itself. And so on its face, on the surface, these are very unrelated things. I think physicists may have tried or thought about relating them physically, but that's not really succeeded. They operate so differently because dark matter, of course, exerts gravity and attracts other matter, including itself. And dark energy is in the opposite sense. It has a negative pressure and it's causing expanding space-time faster and faster. So at the moment, I don't think there is a relationship between them physically, based mostly on our ignorance of dark energy. It is, however, interesting that at this time in the history of the universe, the dark energy in its impact on the universe is about twice as much as the dark matter. So dark matter is about, dark energy is about 2/3 of the universe, and dark matter is about 1/3 of the universe, and normal matter maybe 4%. And in the entire history of the universe, forward and backward, this is the only time that they've been almost equal in their strength. For most of the previous history of the universe, dark energy was negligible. Dark matter and dark matter dominated the expansion. For the future of the universe, dark energy will dominate as the matter gets more spaced out and the gravity weakens. And so this is the one point in cosmic time when these two entities that we don't think are related have almost equal strength. And some people find that to be a coincidence that needs an explanation. Unfortunately, in science, as in the world, coincidences are sometimes coincidences. You don't know when a coincidence is meaningful or telling you some deeper truth about the universe or whether it's just a coincidence.
Yes, thank you, sir.
Okay.
So the next question is that has the universe does universe has center?
No, as I mentioned, every galaxy moves away from every other galaxy. Every galaxy sees the same thing, so you cannot identify a center. And the theory does not require it to have a center. It just says that there was a singular event where obviously every part of space-time and every galaxy and every atom and every radiation wave was part of. But thereafter, there's no way to identify a center.
And the next question is about wormhole.
Just a general question. Yeah.
It is from Dinesh Water. So do wormhole really exist? What's your view regarding this?
The theory of general relativity is about space-time and its curvature. Curvature is based on mass and energy. So the theory of general relativity allows for very interesting things. The theory did predict black holes because when stars die and collapse, the general theory of relativity predicts that you end up with a place where nothing can escape, has a singularity at the center and has an event horizon that you cannot see inside. So black holes are predicted and certainly explained by general relativity. A wormhole, though, is a different thing. A wormhole is a connection between different places in space-time. It's sort of a rupture in the universe, if you like, connecting disparate places. Now, you can, in the theory of general relativity does not preclude wormholes. It's a meaningful concept inside general relativity. You can imagine space-times that are highly curved, complicated topologies that are very interesting and interconnected. And yes, in these complex space-times, you can have wormholes for sure, theoretically. The question really is, are they likely to exist in our universe? And the answer is no, because the space-time of our universe is very flat. The space-time of our universe is almost perfectly flat and actually quite boring. And the only places where that space-time is violated are black holes that we understand. And these are just pieces of the space-time that are just pinched off from our view, essentially. But there's no necessary consequence that they connect with another part of the universe. And in fact, the properties of our universe suggest that's not happening. So I would say the global properties of our universe argue against wormholes. That's not to say they couldn't exist. It's just not considered very likely given what we know about the universe we live in.
So the next question is, do magnetic monopole exist? Is there any heavenly body which has magnetic monopole?
Magnetic monopoles are interesting because they were involved in the beginning of the inflation idea. And in fact, I mentioned two main reasons inflation was developed as an idea to explain why the universe is flat and smooth. A third reason inflation was developed back in the 80s was to explain why we do not see magnetic monopoles, because in the very early history of the universe, when all the forces are merged, essentially, you do predict the existence from this very dense early state of isolated magnetic domains or magnetic monopoles. Not a huge number, but there will be some relic magnetic monopoles out of the very hot, dense early universe. That's what the theory said. And the theory is not completely, clear on the nature of the prediction because it's hard physics. So, and then people looked around, and in physics experiments that have been done before and since, nobody's detected a magnetic monopole. There was one famous detection in the 80s that never was repeated. So people are still looking, but not so much now. And so the absence of magnetic monopoles observationally was another motivation for inflation, because inflation will stretch out that very early space-time so thinly that you don't expect to see magnetic monopoles very densely in your universe, because they've been all distributed vastly in space-time. So the absence of magnetic monopoles was a prediction and a sort of explanation out of inflation. And since then, again, observations have not succeeded in detecting magnetic monopoles. So, their status is unclear. We need data on them to understand better what's going on with a magnetic monopole. Those are very difficult experiments to do, I should say.
So the next question is, can black hole be created on Earth? If so, how? It is from Shreya.
Can be created in what?
Earth. Can black hole be created on Earth?
In art?
Yeah, Earth or our home planet. If so, how?
Oh, in our planet, yeah.
Yeah.
Yes, so in principle, the interesting thing about black holes is black holes could be at any size and scale. If you can compress normal matter to a sufficient point, then it will fit the definition of a black hole. Now, nature, the question is, what can we do, or what could nature do? Nature, the universe, has made black holes all the way up to 20 billion times the mass of the sun. Every galaxy has a massive black hole in it, as far as we know. Most are not active, some are very active. And the biggest, that's some of the research I've done in my career, has been massive black holes in distant galaxies. And so nature makes black holes that are incredibly large. Our galaxy has a black hole that's 4 million times the mass of the sun, sort of medium large black hole. And we've now found black holes 100 in globular clusters that are 100,000, 10,000 times the mass of the sun. And then always, we have known for 50 years, since Cygnus X1, that there are black holes left over when massive stars die. And these are black holes about 4 to 10 times the mass of the sun. That's where most stellar black holes live. If you compress the Earth to 2 centimeters in size, it would be a black hole. So in principle, you can make a black hole any size. Nature doesn't do this. It only makes the ones that are dead star size and up to very big size. The technology to make a black hole is far beyond our capabilities. So even if we wanted, you could make a microscopic black hole, of course. You could take something the size of a tennis ball or squash ball and compress it to smaller than an atom. And in principle, you could turn any object into a black hole if you can compress it sufficiently. We do not have the technology to do so. There was a little story that got into the media about CERN maybe being able to create black holes in collisions of the Large Hadron Collider. And the physicists knew, of course, that this was impossible, not even close. It was impossible by many orders of magnitude, but people got scared enough about it. They had to do the calculation, make it public, tell everyone about it. So no, we cannot, our technology is just vastly incapable of making a black hole of any size.
Thank you. And the next question is a follow-up question about the cosmic microwave background. It says that why can we see the cosmic microwave background in all directions if there is not an edge?
In edge?
If there is not an edge.
What's the last word? Not a
Edge.
what?
Edge.
Spell it. I'm not missing.
EDZE is.
Oh, I think you mean edge, right?
Yeah.
Okay, so I think I said this earlier. There's an edge in time, not space. When we look out in this with the universe with telescopes, we see back in time. We never see an edge in space. It's never been seen. So that you can just say that very clearly out of observation, because as you look out in space, you're looking to the earlier stages of the universe. So what you run out of is not space, you just run out of time as you get towards the Big Bang. And now we've seen so far, we've seen back to the place, to the time when galaxies were first forming. So we've seen past the time of all galaxies to within 500 million years of the Big Bang. And so, but again, no edge anywhere, not needed, not required, and really not possible because you're looking back in time. You're doing history, you're not doing geography. That's the best way to put it. We should probably go to astrobiology or we won't have much time for it.
Yes, there are some questions left, but we can switch to astrobiology, and if time permits, we can come back to cosmology.
Because I do have another meeting that's to go
Yes,
to.
sure.
Okay, so I will summarize astrobiology quickly, quicker than cosmology, mostly because the things we know are clear and the things we don't know are clear and not changing much. Astrobiology is the study of life in the universe beyond the Earth. So as we speak, there's life. We only know of life on one planet, this planet. Astrobiologists feel confident that there is life elsewhere in the universe for several reasons. Because the ingredients for life are everywhere in the universe: carbon, nitrogen, oxygen. Water is quite a common molecule in the universe. So the ingredients are there. And on the Earth, they form quite naturally into complex molecules and eventually cells. We don't know exactly how that happened, but we've made some progress understanding that process. Nothing special or magical about it. And life probably started about 4 billion years ago on this planet, so it happened quite quickly. And more recently, we found a lot of places where we think our kind of biology could evolve. The success of exoplanets to now over 4,000 exoplanets, first one only discovered in 1995, so it's not an old field. These project to roughly an enormous number of exoplanets in the galaxy, one per star. So as many planets as there are stars, at least. But more interestingly, they project to tens of millions, perhaps 30 million habitable Earth-like planets in our galaxy. That is 30 million places where the ingredients for life exist, and there's been plenty of time for it to evolve. And that's where our knowledge stops, okay? So astrobiology lays the table for life in the universe by saying that in our galaxy, and of course all others, ours is not special, there are many, many habitable worlds of roughly like the Earth, in many, not exactly like the Earth, but close to it, where liquid water can be on the surface, where there's a star of the right temperature, and so on. And it's a long-lived star. So that's our knowledge. It's impressive, but it's not a discovery of life elsewhere. We are looking in the solar system, of course, for life. Those are hard experiments. If life exists now on Mars, it will be quite deep underground, beyond what we can do with these rovers and missions we have at the moment. So we may find relic evidence of previous life on Mars with the rovers we plan and have now, but we won't find life existing. The other places we might look for life in the solar system are very far away and difficult to do experiments. That would be Europa under the ice oceans on that moon of Jupiter, Titan, large moon of Saturn, which has liquid lakes, but they're not water, they're ethane and methane. And maybe Enceladus, which is a small moon of Saturn, which has water under the surface and geysers that shoot ice particles into space. And in total, there are probably a dozen moons of giant planets, all in the outer solar system, that have liquid water under their rocky, icy crust and energy, enough energy for life. So there's a dozen habitable spots, not worlds, but spots, locations, or moons, typically, in our solar system. And just it's very difficult and long experiments to get there and do those observations. So we're trying, but it takes a decade to send something to the outer solar system. Beyond Earth, we're also trying, and that's hard too, because to measure life on another planet on a faraway solar system, you're trying to look at a planet that star outshines it by a factor of hundreds of millions or a billion. So you have to suppress the light of the star to see the feeble reflected light from the planet from very far away. And this planet will appear very close to that star. So it's a very difficult suppression to do in a telescope. And then you're trying to smear the light of that planet, the reflected light of its light, to look for the imprint in its atmosphere of biology. On Earth, that imprint is oxygen and ozone, because the oxygen we breathe was created by microbes billions of years ago. So that's the simple next experiment that astronomers will try to do using Earth-like exoplanets that they found. They'll try a very challenging experiment to look at the reflected light of the planet, spread it to a spectrum, and look for what are called biomarkers, that is, tracers of biology. That's biology as we know it, photosynthetic biology. The bigger question of how strange life could be beyond the Earth, if it's not exactly like Earth life, that's an unanswerable question. We don't have any right to assume that biology in the universe will be the same everywhere, that will operate the same ways, that will have the same replicating molecule, that will work with the same cells as our life does, that evolves the same way. We just don't know. So sometimes we don't know what we're looking for. If life on Earth is like, if life beyond Earth is like life on Earth, then we know what to look for. If it's not like life on Earth, we don't even know what to look for. And the experiments are difficult. So that's sort of where the situation astrobiology is. I'd say there are possible ways to look for life in the solar system, but they're expensive, challenging, and take a long time. And we're doing some of them, but the budgets in NASA and elsewhere are too modest to do more than one or two of these experiments. Life beyond Earth will depend on studying the nearest exoplanets that are Earth-like and looking for imprints of life in their atmospheres. And those experiments are getting close. They're going to be done soon in the next few years. James Webb Space Telescope will do some. Big new optical telescopes on the ground here will do some. So within 5 to 7 years, we may actually detect life on an exoplanet by that method. And then, of course, beyond that, there's SETI, the Search for Extraterrestrial Intelligence, which is radio and optical searches for intelligent technological civilizations. Those experiments started in the 1950s and have not produced anything. So there's a big silence, there's no success. That doesn't mean anything because space is big and the signals might be rare and we might not even be able to understand the signal anyway. So people are doing that experiment, and it doesn't take a lot of money to do those experiments, so we should probably keep doing them. But that's probably not how we'll find life in the universe if we do. And it's possible that life is rare, despite having said that we think the possibility of life is there. Until you find a second example, you don't know. It could be that there were some flukes or some unlikely things that happened on the Earth that led to us. We don't know. When you only have one example in science, you can't generalize, you can't make a conclusion. So it is possible that life in the universe is rarer than we think or hope, and then we may never find it. We may not find it at all, or it's just so far away and rare that the experiment is too difficult. But that's a more discouraging possibility, but it's there. We have to understand it. Astrobiology is a very active and successful field of astronomy. It involves interdisciplinary teams, biologists, geologists, planetary scientists, astronomers, physicists. It's very exciting science because it's interdisciplinary. And so it's popular, it's growing. I would say astrobiology as a field is growing, and I can see more students choosing it, more faculty working in it. And so it's very international, of course. Astrobiologists are working in all the main countries doing astronomy. So I'll just stop there so there's time for questions.
Yeah, it is a question from our registration link, and which is from Mosam. Recently, phosphine was detected on the Venus. How its detection leads to the conclusion of possibility of life on it?
So the phosphine detection on Venus is essentially unraveling as we speak. It's very close to being retracted. So unfortunately, this was an exciting story that is now going away. It seems, I'll say what it meant, but let me just first say that the group that reported the detection are now backing off their strong claim because they realize that the molecule the identification they made of phosphine could actually have been other molecules, and they overestimated the strength, or maybe misrepresented the identification completely. So if I were going to make a bet, I would bet this goes away. But phosphine, if detected, is important because on Earth, it does not occur geologically, naturally. It's always associated with biology. And to detect it in the atmosphere of Venus is exciting because it implies there would be biology in an atmospheric region of Venus, which is exciting, and we don't understand how life can occur in a cloud deck of a hot planet at the temperate zone of the hot planet where the temperature is not terrible. But I'd rather not go on about that because I really think that detection is not credible anymore.
So the next question is from Rohan Acharya. What about seasonal methane burst on Mars? Is it a sign of life on Mars?
Yes, methane on Mars is very interesting because on Earth, the methane is associated with biological activity. And so the fact that methane is found coming from the subsurface of Mars into the atmosphere is the potential, I use the word biomarker. It's a potential biomarker on Mars. But then we have to be really cautious. I mean, and also the variability of the methane in geography and over time is exciting. So does detection indicate life on Mars? And I have to say the answer, it's a tantalizing, almost annoying answer that we're just not sure. First of all, the methane concentration is very low. It's parts per billion. It's an extremely small concentration of methane. And when you get methane that small in concentration, much smaller than the methane concentration in the Earth's atmosphere, for example, by a factor of thousands. So when you get methane concentration that low, you have to ask geologists, can you get methane geologically without biology? And they will say, yes, you can. If you have some forms of geological activity, you can get small amounts of methane, and they can change over time because it's related to geological activity. And although Mars is geologically mostly dead, it's not completely dead. There is subsurface activity. There's heating from radioactive decay under the surface. There's modest levels of geothermal activity under Mars. And at the moment, the geologist would say, yeah, we can probably make methane with that property. And so unfortunately, you cannot jump to the conclusion of biology in this case. Because the concentration is so low, there are other ways to get it.
So the next question is, does astrobiology support the theory of relativity?
Astrobiology doesn't really have any comment on the theory of relativity in the sense that astrobiology is really a search for life in the universe and looks to study exoplanets and looks to understand also the history of life on this planet. So there's not a very direct connection with the theory of relativity. I would say does not support or doesn't really have much relation.
And the next question is, how can the movement of sun around the galactic center can predetermine the extinction of life on Earth? How can our fate be related with the movement of sun, stars?
Okay, so you mean that what's the connection of life on Earth with the motion of the sun in the galaxy? That?
Yes.
Yeah. So life on Earth is part of a situation in our location in the universe that has an impact on how life evolves. So the Earth has been around the center of the galaxy dozens of times since the galaxy formed, since the Earth formed. And as it goes around the galaxy, the sun also moves up and down, undulates in and out of the plane of the galaxy. It's called Z-motion. And this motion can take us in and out of denser regions of gas and stars. And so people have speculated that the motion of the Earth and the sun around the galaxy over time has occasionally changed our environment to, for example, increase the impact rate. The impact rate from meteors and debris was very high at the beginning, at the formation, when there was a lot of material left over after the planets formed, but then has declined steadily. It may have gone through a surge one time when planets rearranged in the solar system early on after 500 million years. But then it's supposed to have been modest. But if the Earth and the Sun, in traveling around the galaxy, going in and out of denser regions of stars, gas, and dust, you could change the cosmic environment, and that could lead to impacts, and impacts can cause mass extinctions, and so that disrupts the history of life on Earth. So we're still trying to explain the mass extinctions we've seen in the fossil record. There have been 5 mass extinctions since life emerged from the oceans in the last 500 million years, and maybe others before then, but it's harder to measure. One we think was associated with a meteor impact, the KT impact 65 million years ago, but also there's volcanic geological evidence that there were 2 things going on. There's another extinction 250 million years ago that is almost certainly caused by geology, and that was the Deccan Traps, which is a huge geological event that actually covered your country and the whole of India with lava in a very short time and changed the climate of the Earth dramatically. So we've seen extinctions that are probably caused by geology or an impact, and there may be other extinctions that were caused by our motion through the galaxy. It's just a matter, it's hard to decide these things for sure. The evidence is, there's very little evidence, of course, once you go back in the fossil record.
I think we will take only one questions, or do you have time, Professor?
We can go a couple more.
Sure, sir. So the next question is from our Facebook Live. If there will be a ozone layer in Mars, Venus, Saturn planet, can we live there without any special suits?
Mars? Yeah, Mars is uninhabitable without protection. So the atmosphere is 1% of the density of our atmosphere, and it's all carbon dioxide. So it's unbreathable, and it's very open to radiation, ultraviolet. It's a very dangerous environment. So the only plausible way we can live in Mars is under domes that we protect, and not even just a clear dome that you could look out and see the Mars surface. These are domes we'd have to cover with material to protect from cosmic rays and radiation. Otherwise, the humans would eventually be killed by the radiation. So it's a very hostile environment, and there's really no practical way to make Mars habitable. People talk about terraforming Mars, making it like Earth. That's an incredible undertaking. It's completely implausible and infeasible and incredibly expensive. So it's a nice idea for science fiction, but it's not something we're going to do.
The next question is, can we humans really make life suitable in other heavenly bodies artificially?
Say that again?
Can we humans really make life suitable in another heavenly bodies artificially?
Oh, you mean make artificial life on Earth or elsewhere?
Elsewhere in the universe.
We don't know how life evolves. I guess it's a difficult question to answer because we know so little about life in the universe. Some people have speculated that life, as in the Earth, may go through a stage of evolution where it becomes computational or it goes beyond biology, because we are inventing computers that may be able to think. We're inventing robots that are very capable. We have artificial intelligence. If you put all those things together, you can imagine a form of life that doesn't depend on biology. But that's very speculative. And if it happens here, if we can do it, then why could other biological creatures in the universe not do it? So maybe the universe has many artificial life forms that evolve from biological life forms. But we're now at multiple layers of speculation, because we don't even know if there's life at all elsewhere, let alone what that life might turn into given sufficient time. I mean, these are fun things to speculate, and anything is possible, of course, because it's a big universe, and there are many, many potential biological experiments, and maybe in some of those biological experiments, biology progresses far beyond our capability, and decides that biology, the normal biology, is limitation, and so decides to go towards computation and machines, which can be eternal maybe and live forever. This is, again, speculation, but people do it because why not? Until you have the information, it's okay to speculate. So yeah, we should probably wrap up now. But I appreciate your questions. Great questions. I hope you keep up your interest in astronomy. And yes, at some point in the future, when the world opens up a bit more, I would like to visit.
Yeah, so we would also like to thank you very much. It is such a grateful of you to join us. Like you have been always amazing. So I'm sure that most of us here listening to us have also cleared on various ideas about the Big Bang Theory, expansion of universe, and astrobiology. So Professor, I would like to thank you again, and we are hoping that we could even do such more interactions in coming days as well. Thank you so much for joining us.
Sure, my pleasure.
If any one of our participants would voluntarily like to share their experience about the today's session, you are always welcome to share your experience. So, if any one of you is interested, unmute yourself and share your experience.
Hello everyone, may I share my experience now?
Share.
Firstly, I'm Rupsma Raut, special member at AEN. And if I have to say a single word, how the session went, I would explain it as phenomenal. I mean, an entire session on astrobiology and cosmology, the topic which seek the attention of so many curious minds, and that too by one of the most respected personality in the field. What more would an astronomy lover expect? And for this grand opportunity, firstly, I would like to present huge thank you to our organizing committee and of course to our respected Professor Impey. Well, if I have to share my personal experience, I have been a person who would, dream of stars and space every night. And by simply imagining the universe and the galaxies and the multiverse, I have the spark in my eyes and I can feel that igniting flame within me. And when Professor was talking about the black hole, the dipole moment, big bangs, and the possibilities of life in outer space, I was literally having goosebumps. And I mean, of course, the questions of the enthusiast were equally attention grabbing, and the way Sir answered it, I'm pretty sure most of the curious minds here were, growing to do really great stuffs and all. They actually got their purpose and in the many field, and now for sharing such a precious knowledge which are actually needed to be shared to the youth out there, I would like to present huge thank you to Professor Impey, and also congratulations and thank you to the organizing committee. I hope you'll be doing more and more and more such great sessions. Yeah, thank you.
Thank you, Rupswa. It is such a great word to hear from you because it inspires us to do even better in the coming days. So if there is anyone else, please feel free to open up and share your experience, because it is the one way so that we can even improve in the coming days and make the session interactive. If there is any feedback you would like to give, please feel free and share with us. Or there is a feedback form in the chat box which the Sajan Acharya has sent. You can also use that and give us your feedback in 3 words.
Hello there.
Yes.
It was overall a wonderful session, I would like to say. If Professor Chris is still there, I would like to thank him especially for his valuable time and presence for us. So being in Nepal, and we're studying this small community of astronomy enthusiasts, and the passion he has shown for us, he has managed this time for us and that makes a great impact for Nepalese astronomy enthusiasts. This was an amazing session. I would say much more fruitful than we had expected it to be. We got a lot of our queries answered, and I sincerely wish if we had a longer time or we could manage a next session with him, and then we would be much more benefited. Overall, it was a nice session, and I'm much impressed by the way you guys conducted this session. So a lot of thanks to astronomy enthusiasts in Nepal and Professor Chris Impey. And I expect more fun, more loaded session coming in the future. Thank you.
Thank you so much, Raj Vasil. Yes, so in such a limited time constraint, our professor managed to answer the questions. We know that there were so many questions we have collected from our registration link. We try our best to address all the questions, and even in the chat box, you could see there were questions coming and coming. We tried our best. So
Yep.
if there is any questions that might not have been addressed, we assure you that we'll come up in the coming days and address it in the best possible way. So thank you so much for joining.
How about clicking picture? Yeah, can you see?
Yes. So yes, everyone please turn on your videos because it is such an interesting session and we had a lot of information. So if you turn on your videos, we could take a picture as a memory of such a great day. So please turn on your videos and smile. Sajan, did you take the picture? Yes, thank you. So this, I think we are at the very end of the program. I would like to thank you again for joining us. I was so overwhelmed by all of your participations, and I would like to repeat again that we could not address all the questions. So will come up in the coming days with a lot of time with the Professor Chris or other professor. So stay tuned with us. We are available through our Facebook page. If you have any feedback for us, you can even send us through there. And in the coming days, we are also sharing, we will be sharing more opportunities and interactive program. So stay tuned and bye bye. Take care. Thank you so much for joining.